What if tomorrow already happened somewhere beyond your reach? Imagine discovering your future before making today's biggest decision. Time travel sounds impossible, yet science keeps surprising humanity. For centuries, people dreamed about escaping time's relentless march. Stories imagined machines carrying travelers across centuries within moments. But could those incredible fantasies actually contain hidden truths? The answer begins with a question few consider deeply. Is time truly fixed or more flexible than believed? Most people assume everyone experiences time exactly the same. Modern physics reveals something far stranger than ordinary assumptions. Time does not move identically for every observer everywhere. This discovery changed humanity's understanding of reality forever afterward. Scientists uncovered evidence proving time behaves unexpectedly under conditions. Suddenly, impossible ideas started appearing surprisingly scientifically plausible. What seemed like fiction slowly entered serious scientific discussions. Researchers began exploring extraordinary possibilities hidden within space-time itself. Their findings challenged many beliefs about reality and existence. Some conclusions sounded almost unbelievable, despite strong mathematical foundations. The universe appeared stranger than anyone previously dared imagine. One revolutionary scientist played a crucial role developing answers. His theories transformed physics and redefined humanity's cosmic perspective. Before him, time seemed constant and universally experienced everywhere. Afterward, time became dynamic, relative, and astonishingly flexible. This breakthrough opened doors toward understanding potential time travel. Yet many mysteries remained hidden behind complex scientific questions. To understand them, we must examine time itself carefully. Consider how seconds pass differently during varying emotional experiences. Exciting moments vanish quickly, while boring moments feel endless. Although psychological, this observation hints toward deeper realities beneath. Physical time also changes. Under remarkable circumstances, scientists discovered. Experiments repeatedly confirmed these strange predictions with impressive accuracy. Tiny differences appeared when clocks traveled extraordinary speeds consistently. The faster something moves, the slower time progresses locally. This phenomenon shocked scientists when evidence confirmed theoretical expectations. Suddenly, future time travel seemed less impossible than imagined. If time slows enough, travelers could leap forward dramatically. Years might pass elsewhere while months pass for them. This concept forms the foundation of scientific time travel. Importantly, this idea remains supported by measurable physical evidence. Scientists observed these effects using advanced instruments and experiments. The results consistently matched predictions from established physical theories. Reality appeared to cooperate with astonishingly futuristic possibilities repeatedly. Yet, traveling forward differs greatly from traveling backward through history. Moving into the future seems easier under current understanding. Returning to the past creates puzzles challenging scientific logic. These puzzles involve causality, consequences, and paradoxical outcomes everywhere. Imagine preventing an event that caused your journey originally. Such scenarios create contradictions that remain difficult resolving logically. Scientists continue debating solutions to these fascinating paradoxes today. Some propose alternate timelines branching from altered historical events. Others believe nature prevents paradoxes through unknown protective mechanisms. No definitive answer currently satisfies every scientific concern completely. Nevertheless, researchers continue searching for deeper understanding relentlessly. Their investigations explore black holes, wormholes, and space-time geometry. Each possibility offers intriguing clues regarding temporal navigation someday. Black holes especially reveal extreme behaviors affecting surrounding time. Near them, time progresses differently compared with distant observers. This effect demonstrates nature already manipulates time under conditions. The universe seems capable of remarkable temporal distortions naturally. Could humanity someday learn controlling such extraordinary effects safely? That question inspires countless researchers, dreamers, and visionaries worldwide. Every discovery brings new insights and additional unanswered questions. The deeper scientists investigate, the stranger reality often appears. Time travel remains uncertain, yet possibilities continue attracting attention. In Part 1, we explored time's strange, flexible nature deeply. Now we move into wormholes and space-time shortcuts theory. Scientists describe wormholes as tunnels connecting distant points instantly. These structures come directly from Einstein's field equations predictions. They might connect not only space, but also time. Imagine folding the universe like paper between 2 points. One end could open into another moment in time. This idea remains theoretical, but mathematically possible in physics. Wormholes could potentially allow instant interstellar and temporal travel. However, their existence has never been experimentally confirmed yet. Most wormholes would collapse immediately without exotic matter support. Exotic matter refers to unknown forms of negative energy. Such energy has not been fully discovered or controlled. Quantum physics suggests vacuum fluctuations may contain such energy. These fluctuations happen constantly even in empty space itself. If harnessed, they might stabilize wormholes temporarily for use. But stability remains a major unresolved scientific challenge today. Even tiny disturbances could collapse a wormhole instantly. This makes safe passage through them highly unlikely currently. Inside a wormhole, conditions could become extremely unpredictable rapidly. Gravity, radiation, and space-time distortions may become dangerously extreme. Scientists still study mathematical models for possible stable configurations. Some solutions suggest traversable wormholes might theoretically exist someday. These require energy beyond anything humanity can currently produce. The scale of power needed is almost unimaginable today. Yet physics does not completely rule them out yet. That uncertainty keeps scientific curiosity alive across generations. Another idea links wormholes to black hole structures directly. Some theories suggest black holes may hide wormhole entrances. However, nothing inside event horizons is currently observable directly. Anything entering a black hole may never return back. This makes verification of theories extremely difficult scientifically. Still, mathematical models show fascinating space-time connections potentially. Space-time might contain hidden networks of connected pathways everywhere. These pathways could theoretically link different times together. This raises deep questions about causality and time structure. Could history already be interconnected through invisible temporal routes? Some physicists explore rotating black holes for answers today. These are called Kerr black holes in modern physics. Their rotation twists space-time around them in extreme ways. This twisting may create unusual temporal effects theoretically. However, stability issues remain unsolved in all models. No spacecraft or probe could survive such environments. Therefore, all ideas remain theoretical rather than practical currently. Still, mathematics often predicts reality before experiments confirm it. Many technologies began as purely theoretical concepts initially. Wormholes might follow similar scientific discovery patterns eventually. Scientists continue exploring space-time geometry for deeper understanding. Each discovery reveals unexpected properties of universe structure. Wormholes remain one of physics' most fascinating mysteries, but they introduce serious paradox problems immediately also. If time travel is possible, causality may break down. Events could loop back and affect themselves directly. This creates logical contradictions, known as time paradoxes. The grandfather paradox is the most famous example. It questions what happens if you alter your past. Scientists propose several solutions to avoid these contradictions. One idea is self-consistency across all events always. Another involves branching timelines, forming alternate realities instantly. These interpretations remain unproven but mathematically consistent. Quantum mechanics supports multiple outcomes existing simultaneously potentially. This strengthens many worlds' interpretation of reality theory. Still, no experimental proof confirms these ideas yet. Wormholes therefore remain speculative but scientifically intriguing structures. They challenge our understanding of space and time deeply. Research continues across physics institutions worldwide actively today. Scientists hope future discoveries will clarify these mysteries. In Part 1, we learned time is not truly constant. In Part 2, wormholes suggested shortcuts through space-time itself. In Part 3, black holes revealed extreme time distortion effects. Now we enter the strange world of quantum physics. At quantum level, reality behaves nothing like everyday experience. Particles exist in multiple states until observed directly. This is known as quantum superposition in physics theory. It challenges the idea of a single fixed reality. time at this scale becomes even more mysterious. Some theories suggest time may not be fundamental at all. Instead, time could emerge from deeper quantum interactions. This idea completely changes how we understand existence. If time is emergent, it might be flexible in origin. Quantum entanglement also introduces strange connections across distances. Two particles can instantly affect each other regardless distance. Einstein famously called this spooky action at distance. Such behavior suggests deeper links beyond normal space-time rules. Could similar links exist across different moments in time? Some researchers explore quantum time symmetry in equations. These equations sometimes work forward and backward equally. This raises questions about time's true directional nature. Why does time only move forward in our experience? This is known as the arrow of time problem. Physics laws often do not prefer a direction, yet our reality clearly experiences forward time flow. Entropy provides one explanation for this directionality. Systems naturally move toward higher disorder over time. This creates the perception of irreversible time progression, but quantum physics complicates this simple explanation further. Some quantum processes appear reversible in theoretical models. This suggests time symmetry may exist at fundamental level. If true, time travel equations become theoretically plausible. However, measurement collapses quantum possibilities into reality. Observation forces one outcome from many potential states. This collapse may prevent paradoxical time behaviors naturally. Still, quantum mechanics opens door to speculation widely. Quantum tunneling allows particles to cross impossible barriers. This defies classical understanding of physical movement entirely. Could similar effects scale up to larger systems? Most scientists believe macroscopic time travel remains impossible. Decoherence destroys quantum effects at large scales quickly. Environment interaction forces systems into classical behavior states. Yet research continues exploring quantum gravity theories deeply. These theories attempt to unify space, time, and matter. Loop quantum gravity is one promising research direction. String theory also proposes extra dimensions of reality. These dimensions might hide deeper time structures unknown. If correct, time could be multidimensional rather than linear. That would radically change our understanding of history. Events might exist across multiple temporal layers simultaneously. However, no experimental proof currently supports these ideas. They remain mathematical frameworks awaiting verification in reality. Scientists use particle accelerators to test quantum predictions. So far, results align with standard physics models. Still, gaps in understanding remain significant and important, especially when combining gravity with quantum mechanics together. This is one of physics' greatest unsolved challenges. A theory of quantum gravity could redefine time itself. It might reveal whether time travel is possible or prove it is fundamentally forbidden by nature. Either outcome would transform science forever moving forward. Some interpretations even suggest reality is informational at core. Time could emerge from processing of quantum information. This idea connects physics with computation and consciousness theories, but these remain highly speculative at present scientific stage. Still, they inspire new questions about reality structure. Could future technology manipulate quantum time properties directly? That possibility remains distant, but not fully impossible. For now, quantum physics expands mystery rather than solving it. In Part 4, we explore paradoxes and timeline theories. In Part 1, we questioned whether time is truly fixed. In Part 2, wormholes suggested shortcuts through space-time connections. In Part 3, black holes showed extreme time distortion effects. In Part 4, quantum physics opened deeper layers of mystery. Now we face the most confusing topic in time travel. That topic is paradoxes and the structure of timelines. If time travel exists, contradictions immediately become unavoidable problems. One famous example is the grandfather paradox scenario. Imagine traveling back and preventing your own existence. This creates a logical contradiction in cause and effect. If you never existed, how could you travel back? Scientists have struggled with this problem for decades now. One proposed solution is the self-consistency principle theory. It suggests events always align without contradiction occurring ever. In this view, you cannot change the past at all. Any attempt would already be part of history itself. This preserves consistency across all causal timelines automatically. Another idea introduces the concept of multiple parallel universes. Each decision creates a separate branching timeline instantly forming. Changing the past would simply create a new reality. Your original timeline would remain unchanged and intact always. This removes paradoxes by separating different outcomes entirely. Quantum mechanics supports this idea in some interpretations, known as the many worlds interpretation of quantum theory. Every possible outcome exists in separate branching universes simultaneously. Time travel would then mean jumping between realities instead. However, no evidence confirms these alternate universes actually exist. They remain theoretical constructs within advanced physics discussions. Another theory involves closed time-like curves in space-time geometry. These curves theoretically loop time back onto itself completely. An object could return to its own past position, but stability of such curves remains highly questionable scientifically. Even tiny disturbances could destroy the loop entirely. Physics may naturally prevent such paradoxical structures from forming. This idea is known as chronology protection conjecture. It suggests nature forbids backward time travel altogether completely. Stephen Hawking strongly supported this theoretical protection principle idea. According to it, time machines cannot exist in reality, even if equations allow them mathematically under certain conditions. Reality may enforce rules preventing paradox creation automatically. This keeps causality intact across the entire universe structure. Still, no definitive experimental proof supports any position yet. Time travel remains purely theoretical and speculative scientifically today. Researchers continue exploring mathematical models for possible exceptions. Some quantum effects might hint at retrocausality behaviors subtly. This means future events influencing past conditions potentially. But interpretation remains controversial among physicists worldwide currently. Different schools of thought disagree on meaning entirely. Some reject paradoxes as misinterpretations of incomplete theories. Others believe time travel violates fundamental physical laws absolutely. The truth remains hidden behind complex mathematical boundaries. Experiments cannot currently test these extreme conditions directly. Therefore, debate continues mostly within theoretical physics community. Each model tries to preserve consistency and logical structure. Yet none fully solves every paradox problem perfectly. This keeps time travel an open question scientifically. Philosophically, it challenges our understanding of free will. If the future already exists, choices may be illusionary, or reality may constantly branch into infinite possibilities. Either way, time becomes far stranger than expected. Humanity stands between physics, philosophy, and imagination simultaneously. The final question becomes whether time is linear at all, or whether it is a vast interconnected structure. Some theories even suggest time is an illusion entirely. Only change and motion may truly exist fundamentally. That idea reshapes everything we believe about reality. But science has not reached final conclusions yet. Each discovery brings new questions instead of answers. The mystery of time remains unsolved for now. In Part 5, we conclude with final possibilities. In Part 1 through 4, we explored time travel deeply. We examined relativity, wormholes, black holes, and quantum physics. Each theory revealed new layers of reality's hidden structure. Now we reach the final conclusion of this journey. So, is time travel truly possible in reality today? The answer depends on which direction you consider carefully. Forward time travel is already scientifically proven and real. Einstein's relativity confirms time dilation happens under extreme conditions. Astronauts experience slightly different time than people on Earth. Even GPS satellites must correct for time differences constantly. This proves time is flexible and not absolute universally. Therefore, traveling into the future is physically achievable. However, traveling into the past remains highly uncertain scientifically. No experiment has ever confirmed backward time travel exists. Theoretical physics allows possibilities, but reality remains unproven. Wormholes could connect different times if they exist. Black holes distort time, but likely destroy anything entering. Quantum physics hints at strange temporal behaviors at small scales. Yet none provide practical methods for real-time travel. Paradoxes create serious logical problems for backward movement. Causality must remain consistent for universe stability overall. Some theories suggest multiple timelines may resolve contradictions safely. Others argue nature prevents paradoxes entirely through hidden laws. Stephen Hawking proposed chronology protection against time travel. This idea suggests time machines cannot exist physically, even if mathematics permits them under ideal conditions. Reality may enforce strict limits, preventing causal violations. The universe might protect itself from contradictions naturally. Despite uncertainty, research in physics continues advancing rapidly. Scientists explore quantum gravity and space-time structure constantly. New discoveries could reshape understanding of time completely. Future technology might unlock deeper space-time manipulation methods, or confirm that time travel is fundamentally impossible. Either outcome would transform human knowledge forever significantly. For now, time remains one of greatest mysteries. We experience it moving forward without exception daily, but physics shows it behaves very differently fundamentally. Time slows, bends, and stretches under extreme conditions. This challenges our intuitive perception of reality itself. What we call time may be emergent phenomenon, or it could be fundamental structure of universe. Science has not yet reached final understanding here. Every answer leads to deeper, unresolved questions emerging. This makes time travel both exciting and mysterious. Human imagination continues pushing boundaries of possibility endlessly. From fiction to science, ideas continue evolving rapidly. What once seemed impossible now feels partially real. Future discoveries may change everything we believe today, or confirm strict limits on physical reality forever. Either way, curiosity drives scientific progress continuously forward. Time travel remains a powerful concept in human imagination. It inspires movies, theories, and scientific exploration alike. But real-world application still lies beyond current reach. For now, we understand only fragments of truth. The full picture remains hidden within cosmic mystery. Scientists continue searching for answers across many fields. Physics, mathematics, and philosophy all contribute to understanding. Each discipline brings new insights into time nature, but complete solution still has not been found. The universe continues guarding its deepest secrets carefully. Perhaps time is meant to remain partially unknown, or maybe future generations will unlock its secrets. Until then, we explore possibilities through science and thought, and we continue questioning reality at every level. Time travel may be real in future discovery, or remain forever limited to imagination and theory. The journey of understanding time has just begun. Humanity stands at edge of unknown possibilities today. The future may hold answers we seek desperately. But for now, time remains greatest mystery of existence. Thank you for traveling through time concepts together. Keep questioning reality and exploring scientific possibilities further. The universe always has more secrets waiting discovery, and time may be the ultimate final frontier. The story of time continues beyond this moment,